Well, good afternoon. I'm at school. I'm in room 123 where you'd normally be having your chemistry lessons, and the first thing you'll notice is that your whiteboard has placed over it a smartboard, and we're going to use that almost immediately. So I'm going to use two basic ingredients here, citric acid and baking soda. And I was going to get you to do this one at home because I thought these were readily available in all supermarkets everywhere near you. But when I went into several supermarkets, easy to find, difficult to find, and I had to get this from an online source that I shall not advertise right now, but you know what it was. So let's have a look at these two. One's an acid, one's, well, baking soda. It's correctly called sodium bicarbonate, or even more correctly, sodium hydrogen carbonate. So what we're going to do is have a look at these. We'll look at their formulae. We'll look at what we expect them to do in a chemical reaction, and then we can actually do the chemical reaction and see what amazing things happen. Now, these are not like esoteric things that you only find in a science lab. I did find them in supermarkets, or well, I used to, and of course I use baking soda when I'm making bread, and my mother used to use this all the time, citric acid, when we were preserving fruit, but I guess people don't preserve fruit all that much anymore because they're not as old as I am. So let's have a look firstly at citric acid. So, citric acid, there it is. And citric acid is this weirdo. It's a tricarboxylic acid. Let's see what that means. So we go carbon, 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 carbon. Right? And there's 5 carbons in a row. And then it's actually a C6. So we stick one there. Then it's got something that doesn't affect us very much. It's a hydroxyl group, an OH group sticking out of the central carbon. And then attached to the outer carbons, there are carboxyl groups. That's why it's called a tricarboxylic acid. So all of these have carboxyl groups. Carboxyl groups are made up of an oxygen atom double bonded to the carbon, and then yet another hydroxyl group. So we've nearly finished, but every carbon, of course, in a covalent compound in this molecule has to make 4 covalent bonds, otherwise it doesn't complete its outer energy level. And so here, this one only has 2 bonds, so 2 more bonds. This one, 2 more bonds. And as always in organic chemistry, when you've got nothing interesting to fill in the spaces with, you use a hydrogen. Because all of these chemical reactions take place in water, and there's loads and loads of hydrogen hanging around just to fill up the empty spaces. So here it is. It's a TCA. It is a tricarboxylic acid. And if you've done any biology, which I presume you have this year, because most of you seem to have, this is a really, really important compound. Because the Krebs cycle, that central part of the aerobic respiration process that produces your electron carriers and takes them to the electron transport chain, it's called the citric acid cycle. It's also called the TCA cycle, because there's a whole bunch of TCAs, tricarboxylic acid. And the first TCA that's formed in the citric acid cycle is when you attach pyruvate, or what's left of pyruvate, to the oxaloacetic acid. And that, well, it used to be pyruvate, now it's acetyl-CoA. The acetyl group has 2 carbons. You join it to the 4 carbons of oxaloacetic acid, and it makes, bingo, citric acid, which has 1, 2, 3, 4, 5, no surprise, 6 carbon atoms. So here's your key part. Here's where the link reaction fits in with the Krebs cycle. So in terms of biology, this is pretty amazing. So let's have a look at the other one now, which is baking soda, or more correctly, sodium hydrogen carbonate. And this is a little more simple. It's an ionic compound. It's made of sodium, which of course loses 1 electron and becomes a sodium single positive ion. And then the hydrogen carbonate ion, which is like a carbonate, which would be a double minus, but instead it's got an H attached to it. And so that's that. Now, when an acid reacts with a hydrogen carbonate, what you tend to get is, let's see, there's a hydrogen, and that will come off as a H+, leaving a minus there. It ionizes when you put it in water. And obviously, we're talking about reactions that are happening inside living things, and living things are that enormous percentage of water. So everything that's going on is in water. So here we've got that. And we add that to the hydrogen carbonate ion. And what you get is no real surprise. CO3, take an oxygen off that, and you get CO2, which is, of course, a gas. So you can write the state symbol gas after it. And then the other thing, you've got one oxygen left over, two hydrogens, and so you've got H2O. I ran out of room there. So we can expect a gas to be produced, and that gas will be carbon dioxide. But what I haven't considered is, well, two things. Firstly, there are, three carboxyl groups here, not just one. So this is an acid three times, not just once. So there's a hydrogen that can come off it, there's a hydrogen that can come off it, and we've already looked at that one. So each citric acid molecule will react with 3 formula units of sodium hydrogen carbonate. So that gives you some idea of the molar ratios that are going to be used in this reaction. So, yes, we get a bit more happening here. So when we remove this, we'll get a minus there. When we remove this, we'll get a minus there. And so we get a triple minus ion, which is, of course, called a citrate ion. And that will attach to the sodium here to form sodium citrate. Now, what you'll notice is that I haven't done a chemical formula for that, because that's going to be part of your job. So, here's me wearing a lab coat and safety glasses, because I am, above all, interested in safety and not killing anybody, even you. But now, of course, I'm the only one in this lab. So let's see what we're going to do with this stuff. We'll set this up on my handy chair and point it down so you can actually see something going on. And we've got distilled water, we've got a balance, we've got 100 milliliters of carefully measured out water, a rather dirty beaker, a less dirty beaker, and some weighing stuff. Now I should open these. So here's the citric acid, and I shall weigh out in one of these things exactly, oops, I zero it first, I forgot to do that. I shall weigh out exactly 4.02 grams. And I'll place that extremely carefully into my no longer so dirty beaker and shake it out so I get it all. Then I'll do a very, very similar thing to the sodium bicarbonate, or sodium hydrogen carbonate, as I should call it. And here's my other thingy here, and I zero it, and I take some out, and some out, and some out, and some more out, and I get exactly this much. Oh, I don't know if you can see that. Yes, you can see that. Right. And you should be able to work out how many moles that is, because you've got some masses. You can look up the formulae, or use what I put on the board a minute ago, and therefore work out the formula mass, and hence you can work out the number of moles of this. And so now I mix them together, and there's a lovely reaction, except there isn't. And the reason there isn't a reaction is these compounds can't mix. Remember, in an organic situation, in an organism, in a cell, they would be doing this reaction inside a cell with water in it. And so here is my carefully measured out 100 millilitres of water. And you can see that a gas is being produced. And this is what an antacid does when you swallow an antacid tablet and it goes down into your stomach, because your stomach is full of all sorts of exciting little bits of acid. And therefore, it will react very well with the alkaline sodium hydrogen carbonate. And I want all of this to react. And of course, it's not all going to be reacting. And the reason it's not all going to be reacting is I didn't carefully measure out 3 times as many moles of sodium hydrogen carbonate as of citric acid. In fact, I didn't really take care of what I was measuring out at all. I just did measure it. So I keep stirring it. And I keep stirring it until I stop fizzing, until it stops fizzing. I'm not fizzing. And it's still fizzing. So there's more to react. Now, one of those reactants, citric acid or sodium hydrogen carbonate, is in excess. But I don't know which one because I didn't measure it out carefully. So what you'll have to do is work out how many moles of each of these reactants I've put in here, which one is in excess, and how much there is of excess, whether in grams or moles, or obviously both. And then what I'm going to do is I'm going to use this Bunsen burner over here. It's on the safety flame at the moment. What I'm going to do is evaporate all of the water, and then I'll be able to find what's left. So what's in there is the product. Well, carbon dioxide is a product, but that's not in there. But sodium citrate, that's not a gas. That's an ionic compound. That's in here in aqueous form. And also in here in aqueous form is the reactant that's in excess. So here's your job. 1, find out how many moles of each of the reactants I put in there. 2, work out which one is in excess and how many moles of that are left. And then I'm going to give you the mass of this when I've taken the water out. And if I've taken the water out by evaporation, then what will be left in there is a mixture of the excess reactant and the product. And then you'll be able to work out the mass of the product, and then you'll be able to work out the number of moles of the product, and then finally you'll be able to work out the percentage yield of the reaction. Good luck with that!